In this session, we are going to see about the finite automata and deterministic finite automata. So first we will see what is a finite state automata. So the finite state automata is a machine that given an input jump through the series of states according to the transition function. Okay, based on the transition function, what we will do, we will jump this series of states for the given input. So it is a model of behavior composed of state, transition, and the action. It is a model of behavior composed of states, transition, and actions. So the finite state machines are widely used in modeling of application behavior, designing of hardware digital system, then software engineering, and study of computation and the languages. And this finite automata is a mathematical model of a system with discrete input and the output. And same time it consists of finite set of states and a set of transition that occur on an input symbol chosen from the alphabet set sigma. One of the state is called initial state where the automata begins, and there can be one or more final states. So based on the input or based on the language what we have taken, it can vary, but it should contains only one initial state. For example, we can see the operation of switch. So already we have seen this in the introduction of automata, how the switch works. So in the operation of switch, so there is only two states, right? One is the on state. So on state, we can consider this is the on state and this is the initial state, and another one state we can consider this as the off state. Okay, so okay, when we press the switch, so it is the input. We are pressing the switch. If it is on means it is off, and if it is on means it is pressed. So whenever we are pressing the switch, the state will vary. It may be on or off. The next, there is two types of finite automata. One is the deterministic finite automata and another one is a non-deterministic finite automata. So in a deterministic finite automata, from each state for each simple, there is exactly one transition. Okay, for each state for each simple, there is only one transition. But in a non-deterministic finite automata, for each state, for each input symbol, we can have a zero or more transition. Okay. So in a deterministic finite automata, for each symbol, there is exactly one transition. But in a non-deterministic finite automata, it can have a zero or more transitions. And in a deterministic finite automata, it doesn't have a epsilon transition. But in a non-deterministic finite automata, it has a epsilon transition. So this is the difference. Then the picturization of finite automata. So a finite automata can be picturized as a finite control which is on some state from the queue, and it has a reader. So this is a tape. This is a tape. Okay. So this is the tape and this is the tape reader. It will read the input one by one. Okay, and in a finite control, it contains some states from the queue. So based on the input value, what will happen? The state will vary. So in one move, the finite automata can able to do it can able to do uh, reading. So that is, it will read the input symbol. Then second one, it moves its head position to the right side, and third one, it moves to the state as defined by the delta. So at a time it can able to do these three operations. It can read the input symbol, then it moves its head one position to the right, then it moves to the state as defined by the delta. So briefly we will see about the deterministic finite automata. So a finite automata model that allows exactly one transition from a state on an input symbol is called deterministic finite automata. Okay, so allows exactly one transition from a state on an input symbol is called as a deterministic finite automata. An input string accepted by a DFA if it reaches one of the final state on reading the input. Okay, if it reaches the final state, so it is accept the particular language. Okay, so we will see the example for this. Okay, uh, so the first example we are going to see here is how to design the DFA to accept the string that starts with A and end with B over sigma is equal to A comma B. So here we have taken the input symbol as the A comma B. Okay. So first we will draw the transition diagram. So here when the DFA accepts the string, if it starts with A and it ends with the A. So what can be an example string? AB. So here it starts with A and end with the B. Then next it can be AABAB. So it starts with A and end with B, and in between A and B we can have a multiple number of A's and B's. So based on that we have to draw. So first the initial state. So Q naught, I am considering Q naught as the initial state. So we need to denote the initial state like this. Okay, this is the initial state. So what should be a starting string? A should be a starting string. So from the initial state to the next state, Q1. So what we are doing, we are giving the transition for the input symbol A. The final next state, so that is the Q2. So what should be a last symbol? B. So that is it start with the A and end with the B. So B. So it starts with A and end with the B. So if you are going to end with the B means it can be a final state. So the final state should be denoted with the double circle. Okay. If the state is denoted with a double circle, it is a final state. So in between A and B, so you can see this. In between A and B, what we can have? We can have a multiple number of A's and B's, right? We can have a multiple. So after this A also, we can have a A. So I'm creating the loop for this state A. And for here also I'm creating the loop for the B, because the input can be like this also. A, B, 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 B. So it will work here. Okay, then for this symbol AAB, after again there is a A. So what we can do, from Q2 to Q1, we can create the transition for the input symbol A. Okay, so this is the transition diagram. So for example, we will check with some other example. No, we can check with this example. So first A, so Q0 to Q1, so input symbol A. Then again there is A. So it will work in this loop Q1. So again here is a A. Then next what is the symbol? B. So Q1 to Q2 it is a B. Then again B. So it will stay in the same state Q2 B B B. So now you can see it starts with the A and end with the B. So this is a transition diagram. Okay. Then we will see the transition table. This is a transition table. So in a transition table, here we have to specify the states. So here totally 4 states, right? Totally three states are here. So it is Q0, Q1 and Q2. And here we have to specify the input symbol. Here our input symbol is A and B. And this is the initial state and this is the final state. Q2 is the final state. The next we can check the transition Q0 comma A. So what is Q0 comma A? It is going to the next state Q1. Then Q0 comma B. So from Q0 for the input symbol B, it doesn't have a transition, right? It doesn't have a transition, so it is null. Then from Q1 to A, it remain in the same state Q1. Then Q1 to B, it is going to the next state, it is the Q2. Then Q2 comma Q2 comma A. So it is going to the next state Q1. Then Q2 comma B. So it is staying in the same state. So it is Q2. Okay. Suppose. Okay. Suppose. Uh, suppose if it is B. Okay. If you are transmitting the value B, so the state is Q3. Okay, what will happen? We can't able to follow the statement what is given here, right? So it will go to the dead state. So this is the dead state. And again, if you are trying to transmit A comma B means it is a dead state. So here we can add this also, Q3 state. Okay, so from Q3 to A, it is remaining in the same state Q3. Then Q3 to B also it is remaining in the same state. And from Q0 to B, so it is Q3. Okay, so this is a transition diagram and the transition table. The next, the formal definition of the finite automata. Okay, so a finite automata can be formally denoted by the 5 tuples. So that is Q. Q means it is a set of states. Then sigma, it is the input alphabet. Then delta, it is a transition function. So how we are checking the transition function? State comma input symbol, it will give the next state. Then Q naught is the initial state and F is a set of final states. Okay, so we will write the formal definition for this. So the formal definition for this is, what is the first one? It is a state, set of states. So what are the states we have? It is Q0, Q1, then Q2 and Q3. The next input symbol. So what is the input symbol? 0 and, sorry, A and B, right? Input symbol is A and B. The next transition function, so we can write it later. The next initial state, so delta here. Then initial state is Q0. Then F is a set of final state. So it set of final state. Q2 is a only one state here. So Q2. So if it is a set of means we have to mention in the curly braces. Then we will see how to write the delta. So where delta is defined as delta of Q naught comma A. Delta of Q naught comma A. So we have to write it from this table. What is Q naught comma A? It is Q1. And what is Q naught comma B? It is Q3. So it is equal to Q1 and delta of Q naught comma B is Q3. Then next we have to write for Q1 comma A and delta of Q1 comma B. So what is Q1 comma A? Q1 comma A is Q1, Q1 comma B is Q2. So Q1 then Q2. Next we have to write delta of Q2 comma A then delta of Q2 comma B. So what is Q2 comma A? It is Q1 and Q2 comma B is Q2. So it is Q1 and it is Q2. Then next we have to write Q3 comma A and delta of Q3 comma B. So what is Q3 comma A? It is Q3, then Q3 comma B is also Q3. So it is also Q3 and this is also Q3. So this is a formal definition of the finite automata.